Okay, students, can you all hear me? And first, let me share the screen. Okay. Can you hear me and see the screen now? All right. Thank you very much. Right. Okay. So let's start today's review session. But before that, just want to let you know this, right? Now, I will I will carry on this session for maybe more than an hour, right? Maybe 1.5 hours or maybe 2 hours if you can hang on, right? Okay, so let's see, right? So definitely I'm going to do it for 1.5 hours, right? Okay, and let's see how it goes afterwards, right? And now if you have another class, that means at 1 p.m. if you have a class, please go to that class, right? Go to that session, right? Because I will record this and post it in YouTube, right? Okay, so don't worry about it. So if you have another class to attend at 1 p.m., uh, log out of this session and go to that new your regular class at that time, right? Okay. Okay. So right. So let's discuss today's questions, right? So I have to start from question number 16. Right. Question number 16. For a t curve with degrees of freedom, find the value of t point point 1. Okay, so we need to find t point 1. Okay, for degrees of freedom, 11. Okay, now just like the normal table, right? There's a thing called the t table. Okay, we know that actually, right? We learned it. So in the t table, to find an exact value you need, right? You need these two quantities, this value and especially the thing called the degrees of freedom. Okay, so I usually write it like this. So 0.1 comma then the degrees of freedom, right? So that's how I used to write it. Okay, so I don't write this like t.01 degrees of freedom 11 separately. I will just write it like this when I'm doing some other questions, right? So keep in mind my notation as well, right? Okay, now what does this mean? So if you have, let's say t alpha, right, comma n minus 1, this means now the t distribution is also like the normal distribution, but slightly different. We say that it has, heavy tails at the end, right? Just like the normal table, but a slight difference that, uh, the at the tails, it's more thicker, right? Whereas if I draw the normal on top of this, the normal tends to looks like this. Okay, that means you can see at the tail the normal distribution, you know um, drops down very quickly, right? Whereas the t distribution has, still heavy tails, we call it. The word for it is it still have heavy tails here, right? Okay, the tails are thicker than the normal distribution. But anyway, the thing is, uh, how to look these t values in the table, and it's very easy. Okay, so let me go to the t table. Okay, we have it here. Okay, in your formulas and table sheet you have here's t table, right? Okay, let me rotate it. Okay, now it's much more clearer. Okay, now here's the t table, and you can see there are values here, right? So t.1, t.05, t.025, right? And t.01, t.005, and so on, right? And then there's this degrees of freedom column. Okay, now you you are looking for, in this case, t.1 comma 11, right? So t.1 is this row, right? Is this, sorry, is this column. Okay, now where should you stop? The degrees of freedom helps you there. We need the degrees of freedom to be 11. So T.1 is this column, and we need T.1 at degrees of freedom 11. So our answer should be 1.363. Okay, 1.363. Let's see whether we have such an answer. Yes. So question number 16, answer is A. Okay. Question number 17. Question number 17 is the same. It's asking for a T curve for T.05 with degrees of freedom 4. Okay. So what you're basically looking for is when you have 0.05 probability to this side with degrees of freedom 4, the value here is T.05 comma 4. Okay. That's what it gives you, right? If you look in the table, okay, let's look for this in the table. Okay. Now, if you're not sure what this thing is giving you, this picture on top will help you to understand it, right? So it clearly says T alpha. That means when you have, you see this alpha probability marked towards the right hand side, right? When you have alpha probability to the right, T alpha value is what this thing is going to give us, right? That means the value here, right? Value here, right? When you have alpha probability towards the right, the value here on the t-axis now, right, is given as t alpha. Okay, that's what we find in this table. Okay, right. Now let's see T.05 comma 4. T.05 is this column, the second column, and degrees of freedom 4. So you have this value 2.132. Okay, so the answer is 2.132. Okay, so yes, so the answer is going to be D. 17, answer D. Okay, 18, I'm going to do it very quickly. It's the same, right? T.01, degrees of freedom 20. T.01, degrees of freedom 20. T.01 is here, and we need to go for degrees of freedom 20, which is here, right? 2.528. 2.528, which is answer C. Okay, question number 18, answer is C. Okay, right. So those three are very easy, right? You just need to look in the table, right? T table. Now there will be one question like this, right? Okay, not more than that, but there will be one question like this, finding these t values. Okay, so be ready for that, right? Okay, next question. Question number 19. Now, when I'm discussing this, if you have any questions, right, you can speak up, right? No problem, right? Okay. Question number 19. A sociologist develops a test to measure attitudes about public transportation, and 27 randomly selected subjects are given the test. The mean score is 76.2 and their standard deviation is 21.4. Assume that the population is normally distributed. Find a 95% confidence interval for the mean score of all such subjects. Now, in chapter 8, you simply need to remember very few things, right? Under confidence intervals or interval estimations, right? First thing is what? How do we create that confidence interval? You take the point estimate, you add the margin of error, subtract the margin of error. That's how you create, this is the basic idea of creating the interval estimation, right? So that means this length length is equal to 2 times the margin of error. Okay, so this helps in some questions. We saw that, right? And beyond this, there are two main equations that we need to create confidence intervals, right? Or interval estimates, right? So confidence intervals, right? Or interval estimates, both are the same, right? Interval estimate. There are two main equations in the syllabus. One is x bar plus or minus z alpha over 2 sigma over square root n, and the next is x bar plus or minus t alpha over 2. I'm going to add the degrees of freedom here as well, comma n minus 1, okay, s over square root n. Okay, now what is the difference between these two? If sigma, or the population standard deviation, is known, you use this. If sigma is unknown, okay, instead the sample standard deviation is known, you use this. That's the main difference. Okay, there are other things, but you can do the questions simply at this level by looking at the standard deviation. You can pick the correct equation out of these two simply by looking at whether you know the population standard deviation or not, right? Now, when you read this question, okay, now let me go back a little bit, right? Okay, look, look at this, right? This is question number 11, right? So it gives the question and assume that, look at this, sigma is 3.8 pounds. That means in this question number 11 that we did before, sigma was known, right? That means the population standard deviation was known. So we use this equation to find the answer, okay? Now, this question, read this very carefully, right? It's very similar, but the only difference is this. 27 randomly selected subjects are given the test. Their mean score is 76.2. That means their mean score means this random samples, right? Sample of 27 people's mean is 76.2, and their standard deviation. That means this samples, right? This sentence is talking about this sample of 27 people, right? It's, sorry, their standard deviation is 21.4. Now, let me write down the information given here, right? So question number 19. There are 27 randomly selected people, so sample size is 27. That should be clear, right? Then what else is given? Sample mean, right? The sample mean x bar is 76.2. Now the question, is this 21.4, is this the population standard deviation or sample standard deviation? Because depending on that, your whole answer will change, right? If the population standard deviation is given, you use one equation. If the sample standard deviation is given, that means if the population standard deviation is not given or unknown, you use another equation. Note that this standard deviation is what? For this sample of 27, it's clearly stated here, right? And their standard deviation is 21.4, right? So this is not a population standard deviation. Instead, we know S, right? S is 21.4. Now, out of these two equations, once you have this information, right? Which one should you pick? Is it the first one or the second one? This is very important in the question. That's why I'm emphasizing, right? If you use the wrong equation, you will get the whole thing wrong in the end, right? So sample standard deviation is given, and that means population standard deviation is unknown. That's when you use this one, okay? So this is out of the way for this question when you see this, right? Okay, when you see that the sample standard deviation is given, you have to use this equation. Okay, now let's see how to proceed. Okay, so let's take that equation, x bar plus or minus t alpha over 2. I would write degrees of freedom along with this as just to remind myself, right? The degrees of freedom is n minus 1 always, right? Times s over square root n. Okay. Now, you have everything, right? X bar is given, s is given, n is given. Now, what is t alpha over 2 comma n minus 1? What is alpha? To find alpha, we have to look at the confidence level, right? So what is the confidence level? Find a 95% confidence interval, okay? So we need to find a 95% confidence interval. That means our alpha is what? If you are 95% confident, that means rest of the 5%, we are not confident or we are not sure, right? That is the error that we are allowing, right? This error is alpha, right? Now, this 5% written as a decimal is going to be alpha. Okay, so 5% means if you write it as a decimal, it's 0.05. Okay, 5%, you divide it by 100, you will make it a decimal or a fraction, right? So alpha is 0.05, but what do we need here? Alpha over 2. So alpha over 2 is 0.05 divided by 2, which is 0.025. Okay, and remember, the degrees of freedom is always n minus 1 for these questions. Always n minus 1. That means sample size minus 1. So we have a sample size of 27. So degrees of freedom is going to be that minus 1, which is 26. Okay. Now we look in the t table for this value. T alpha over 2, we found that it is 0.025, right? Comma n minus 1, which is 26. Okay. Now let's look in the t table for this value. T.025 is here. Degrees of freedom 26. We have 2.056. Okay. Now we have everything we need. Now we simply need to use this equation and we know x bar is given, s is given, n is given. We just found this value, which is 2.506, right? Using the table. Now let's plug in the values. So I will do it here. Okay. So what is x bar? 76.2 plus or minus t alpha over 2 comma n minus 1 is actually alpha is 0.02, alpha over 2 is 0.025, n minus 1 is 26, and t 0.025 comma 26 we found from the table that it is 2.056 times s. S is 21.4 divided by square root n, which is 27. Okay. Now, note that here degrees of freedom is n minus 1, okay? But here it is n, right? Here it's straightforwardly n, this value. But when you're taking the degrees of freedom, it is n minus 1, right? When you look in the table, you don't look for 27, you look for 26 degrees of freedom, right? But here, when you're in the division, you have square root n, which is simply 27, okay? Okay. Now, afterwards, it's simply using the calculator properly. Okay, so 76.2 plus or minus the answer for this part, right, is 8.467. 8.467. Okay, use the calculator and find it. You will see that it is 8.467, right? Now what do? Next, you simply add this part to 76.2 to get the upper value of your confidence interval. You subtract this value from 76.2 to get the lower value of your confidence interval, right? So when you first subtract it, 76.2 minus 8.467 will give you 67.733. Then to get the upper value, you take this and add this value, right? So 76.2 plus 8.467 will give you 84.667. Okay. Right. Now let's look at the answers. Okay. Now you can see that the answers are correct to one decimal place. So let me write it correct to one decimal place. So 67 point, when you're writing it correct to one decimal place, you have to look at the second decimal place, right? If it is 5 or more, you add 1 to this. If it is 4 or less, you don't do anything, right? So here you have 3. So 67.73 remains at 67.7. 84.66. Now this is greater than 5, so I have to add 1 here, right? So when you round it, it becomes 84.7. Okay. Okay, we have answer now, right? It's answer D. Okay. Question number 19, answer D. Okay. Question number 20. A savings and loan association needs information concerning the checking account balances of its local customers. A random sample of 14 accounts was checked and yielded a mean balance of $664.14 and a standard deviation of 297.29. Okay. Now note that this is not the population standard deviation. It is the sample standard deviation. Why? Because this sentence is talking about this random sample of 14 accounts, right? This 14 accounts of, this is the random sample, right? These 14 accounts had a mean of this 664.14 and standard deviation of this. So these are what? Again, sample things, right? So when you see that, you know which equation to use. Let me write down this. Question number 20, right? Sample size 14. Okay. It's here, right? Sample of 14 accounts, right? And the mean of that sample, which is X bar, is 664.14, and S is 297.29. Okay. Now, another thing, right? If you are confused of how to find the sample stand, like whether this thing is the sample standard deviation or population standard deviation, there's one more point. That is, usually, right, if they are giving you the population standard deviation, they will directly use the word population standard deviation, or else they will directly use this notation sigma, right? This is this is one of the main points that you can capture whether it's a population standard deviation or not, right? Okay. If in the question sigma is given like this, right, you use the equation for that, right? But in this question, there's nothing mentioned about the population standard deviation or nothing mentioned about this notation sigma, right? And if you read this carefully, you can clearly see that you should be able to understand that this sentence is not talking about the population, it's talking about this sample of 14 accounts, right? Its mean is this, its standard deviation is that. So therefore, this is not a population standard deviation. This is a sample standard deviation. Okay. So once you have it, right, you know which equation to use, right? Out of these two equations, now you have to use again this. Okay. S over square root n. Okay. X bar plus or minus z alpha over 2 sigma over square root n is out of the way, right? This is the one to use. Why? Because of this, right? When the sample standard deviation is given, you have to use this. Okay. Now, everything is given. What we need to find is t alpha over 2 comma n minus 1. Now, what is alpha here? To see that, we have to look the confidence level, right? The confidence level here is how much? 90% confidence interval, right? So we need to create a 90% confidence interval. So the confidence level is 90%. That tells us that the error level that we are allowing is 10%, right? If we are 90% sure, 10% we are not sure, right? Therefore, this is alpha. If you write this 10% As a decimal, we call it alpha or type or the error that we are allowing, right? So 10% as a decimal is 0.1, but here we need alpha over 2. So let's calculate alpha over 2. You simply divide this by 2, okay? So if you divide zero point 0.1 by 2, you will get 0.05, okay? And the degrees of freedom is very easy. It's going to be 13. Why? Because the sample size minus 1, okay? Now let's look in the t table, okay? We have to look for t.05 comma 13 now, okay? t.05 comma 13. t.05 is here, and 13 is 1 point, it's here, right? 1.771. 1.771, okay? Right. So let me plug in the values now. Okay, I will do it here now, right? So this is the equation to use. Now we have everything. Okay, we just found the t value. X bar, S, and N are given in the question. Okay, so X bar is 664.14 plus or minus t alpha over 2 comma n minus 1 is t.05 comma 13 for this particular question, and we found it using the table. It is 1.771. S is 297.29. Okay, again it is straightforwardly given. Okay, S is 297.29 divided by square root n, which is 14. Okay, sample size, which is 14. Now the statistical part is done. You simply need to use the calculator properly now onwards, right? So 664.14, okay, um okay, plus or minus, okay, when you do this part, right, when you calculate this part, you will get the answer as 140.713. Okay, so you calculate this part separately, add it to this, and subtract it from this. You will get the two values of your interval estimate, right? Okay, so let me write it now. Plus or minus 140.713, which will give me the two values, 523.426 to 804. 426 is the smaller value. That means take this and subtract 140.713 will result in this answer. And 664.14 plus this will result in 804.853. Okay. Now I'm always getting my answers more than one decimal place than I need in this question, right? So the question is, sorry, the answers are given up to two decimal places, right? So I'm taking, you know, uh, taking my answer up to three decimal places so that I can round it to the second decimal place, right? So when I round it to the second decimal place, I will get 523.43 here because I have 6 in the third decimal place. And for the other one, 804.85 because the third decimal place is 3, right? And the answer for question number 20 is D, okay? Right, okay. Question number 21. Now, question number 20 is the last question from chapter 8, okay? Now, you can see what you need to know, right? There are quite a few things that you need. Just, you don't, you simply need to know very few things to answer these questions. Those two equations are very crucial. And the other thing is, other thing that we needed when answering these questions from chapter 8 is the length is equal to 2 times the margin of error, right? Length of the confidence interval is 2 times the margin of error, right? Okay. So those 3 points will help you, answer a lot of questions, more than 90% of the questions from chapter 8, right? So, right. So try to take these things into your head, right, when you're doing these questions, right? Okay. So that it will be easy in the exam, right? Now, question number 21, this is the start of chapter 9, actually, right? Okay. Question number 21. The maximum level of a certain toxic chemical in vegetables has been set at zero point 0.4 parts per million. A consumer health group measures the level of the chemical in a random sample of tomatoes obtained from one production to determine whether the mean level of chemicals in these tomatoes exceed the recommended limit. Determine the null and the alternative hypothesis. Now, chapter 9 is about hypothesis testing. Okay, it's what do hypotheses do? It tests a hypothesis, right? Now, when it comes to hypothesis testing, right, first step is to build the hypothesis. Every hypothesis have two parts. One is called the null hypothesis and the other is called the alternative hypothesis. Okay, now the null hypothesis is very easy to write because it always, right, here we are testing always, we are not testing for any other thing rather than a population mean, so you can always use mu, right? Mu is the population mean. The null hypothesis says mu is equal to some value, right? It can be 2, it can be 3, it can be anything. Let me call it mu naught, right? Okay, and the alternative hypothesis is the one that is changing. It can take three different ways, right? Alternative hypothesis can look like this: mu greater than mu naught, mu less than mu naught, or mu not equal to mu naught. Okay. So depending on the alternative hypothesis, we have three types of hypothesis tests. Okay. One is called the right tail test. The first one is a right tail. This is called the left tail. This is called a two tail. Okay. Now, um, okay. Now, first thing is to build up these two null and alternative hypotheses. Okay. So this question is about building up the null and the alternative, right? Now, out of these two hypotheses, null, I told you, is very easy. It always have the equality sign. Okay. And the alternative is the one that brings the new information, right? For example, if you read this question, right? Now, there is a certain amount of toxic levels that tomatoes can have, right? Without harming our body, right? So that they say it's zero point 0.4 parts per million. Okay. So so the government or the CDC, maybe someone, right, recommends it's okay to have zero point 0.4, but not more than that. Okay. Now, what is this consumer health group is trying to do? They are trying to measure whether these certain farms, tomatoes have more than this much of toxic level, right? Now, they can come to two conclusions in the end, right? They can say that these tomatoes have more than this recommended amount of toxic level, or it's okay, that means it have zero point 0.4 or less, right? Okay. Now, where would the new news come in, or new information? A new news will appear. A new news will appear if this zero point 0.4, right, if the mean, right, mu of these tomatoes is more than this toxic level, right, then it's going to be a big news, right? It's not consumable for people, right? You have to either discard all of those tomatoes, right? uh, and make the production again, right? So so this is a new news, right? Always this thing that you are testing, right, goes to the alternative, right? So the null and the alternative here are going to be this. Null is very easy. That means no change. The process is going on as usual. That means mu is zero point 0.4 parts per million. That means null is is not going to give us a news, right? A new news, right? If the null is correct, there's nothing new, right? The production is going okay, right? There's no there's no exceeded amount of toxic level in these tomatoes, so they can carry on their work nicely. So that's it, right? Now, what is alternative? Alternative is the one that this food company is testing. That means they want to test whether, right, the health group measures the level of chemicals in the random sample of tomatoes obtained from one producer to determine whether the mean level, that's why we use mu, right? Because it's about mean, right? Mean level of chemicals in these tomatoes exceeds the recommended limit. So they are testing whether it is okay or whether it exceeds this zero point 0.4 limit. Okay, so that's what they're testing. Okay, so this is going to be your null and alternative. Okay, so null is very easy. It's always the equality, but the alternative is the one that changes depending on the question, right? Now here they are testing whether this mean level exceeds this particular amount. So alternative is going to be mu greater than zero point 0.4. Okay, now at the same time I will tell you this as well, right? There are three types of tests, right? There are three main categories of hypothesis tests, right? It is very important to know this because the calculations later on will change depending on, slightly change, right? Not, in a big amount. The calculations will slightly change depending on the type of test, right? So there are three types of tests: right tail test, left tailed, and two tailed. Okay. Now, out of these three, right, this hypothesis test goes to the category of right tail test. Okay. Now, the meaning is here. Here's the meaning, right? Now, when you are categorizing this as right tail, left tail, or two tail, you're looking at this. You're looking at the question like this: when do we reject the null and go to the alternative, right? What kind of values of, let's say, the sample mean, right? Now you have some statement about the population mean here, right, in the hypothesis, right? Now to test this we use the sample. Now what kind of sample means would tell me to reject the null and go to the alternative? Small sample means or large sample means? For example, if your sample mean is zero point 0.4, it's better to stay at here, right? If your sample mean is zero point 0.3, still, yeah, it's better to stay at the null. If your sample mean is 0.41, still it's okay to stay at the null. But if your sample mean is zero point 0.5, you may need to think about the null because the null is saying mean is zero point 0.4 and the alternative is saying mean is greater than zero point 0.4. So if your sample mean, if you look at the sample mean, right, if it is like zero point 0.5 something, you may need to go here, right? If it is like zero point 0.6, if your sample mean is like zero point 0.6, you have more evidence to reject the null and go here. If your sample mean is like zero point 0.9, well, you have very good information or evidence to reject the null and say that the alternative is correct. That means reject the null and go to the alternative, right? Now, that's what we use to, you know, uh, categorize these tests here. as right-tailed because we reject the null and go to the alternative in this case, right? When the alternative is like this, we reject the null and go to the alternative when your sample mean exceeds some point, right? Okay, that means when you have higher and higher values, it will support the alternative, right? So the rejection region, we call this, is going towards the right. That means we reject the null and go to the alternative when we have higher values of our statistic, right? So that's why this is called a right tail test. Okay, but we don't need this here, but we will need it later on to answer some questions. That's why I explained it at this point, right? Okay, so once we write this null and the alternative, we have the answer, right? The null is this, alternative is this, so the answer is going to be B. Okay, question number 21, answer B. Okay, question number 22. The recommended dietary allowance RDA of vitamin C for women is 75 milligrams per day. So this is the recommended amount. Okay, so I need to write the null and the alternative. So the recommended mean amount is 75 milligrams per day. Okay, so I don't need to worry about the null too much, right? The alternative is the one that changes everything, right? Null always have the equality. Okay, mu is equal to 75 milligrams, right? That is the recommended amount. Okay, a hypothesis test is to be performed, right? A hypothesis test is to be performed to decide whether adult women on average get less than the RD of 75 milligrams per day. So what are we testing? We are testing whether these women are getting less than 75 milligrams per day, right? So that's why this contains the new news, right? That means if the alternative is correct, it's a big news, right? These people are not getting the recommended amount of vitamin C, so the government or health companies have to do something to, raise their health level up and may get them the necessary amount of vitamin C, right? Okay, vitamin C per day, right? So, um, so this always contains the new news, right? The alternative is the one that uh, the scientist or the researcher is interested in, right? If if the now in the end, right? We haven't done this part yet, but you can see that out of these two hypotheses, one should be correct and one should be wrong, right? Okay. If this is correct, it says the mean level is equal to 75 milligrams. That means they are getting the amount they need, so nothing to do specially, right? These people are getting the necessary vitamin C amount regularly, right? If the null is correct. But if the alternative is correct, that's a big news, right? Okay. So, right. Now, here, um, we have the answer now, right? So 22 answer is going to be A. Okay. Now, again, note that this is a left tail test. Why? We have more evidence, right? Now, if your sample is giving you smaller values, right? That will support the alternative, right? That means you reject the null and go to the alternative. You reject the null and say that the alternative is correct when you get smaller values, right? Smaller your sample statistic, better the chance of rejecting the null and going to here, right? Okay. So smaller values will tend to reject, smaller sample statistics will tend to reject this null and go to the alternative. So the rejection region is towards the left hand side, right? So that's why we call it a left tail test. Okay. Okay. Um, right. Question number 22 is done. 23. The mean credit and debit among households in one state is dollars 8,400. A hypothesis test is to be performed to decide whether the mean credit card debt for households uh, in the formerly affluent town of Rich No More differs from the mean credit card debt for the state. Okay, right. So here we are testing something like this. This the mean credit debt among households in one state is this, right? So the mean level is this, okay, $8,400. Okay. Now a hypothesis test is performed to decide this mean credit card debt for households in the formerly affluent town of Richnomore differs from the mean credit card debt for the state. So this alternative hypothesis test, so this is what we are expecting, right? But the hypothesis is performed to test whether for this particular town, this mean level is deferred from this amount. You see the word differ, right? Now, in the previous case, we check whether the vitamin C level is less, right? So mu less than 75. In the first question, we checked something like, the toxic level of tomatoes is greater than some level, right? This was our alternative, right? So this became a right tail test. This became a left tail test. And here we are testing whether the mean level differs from this amount. That means whether differ can happen in two ways, right? We are not testing whether it is less or greater than greater than some toxic level or less than the amount that the vitamin C amount that a person should get. But here we are testing whether this mean level differs from this amount, right? So that means the alternative should be mu not equal to some value. The value is 8,400, right? Okay. So this is a two-tailed test. Okay. Okay. At this point, I can give you the answer, but let me further explain why this is a two-tailed, right? So 23 answer is going to be D, right? Now, why is it two-tailed? Because we can reject the null and go to the alternative, right? The alternative is saying the mean is different from this amount, right? 8,400, the mean is simply different from that, right? Now, the mean we can say that the mean is different from 8,400 if we get a very high value for the mean, or if we get a very small value for the mean, still it's a different, right? We are simply testing whether it is different, right? We are not testing whether it is high or low. Instead, we are testing whether it is different. So we can reject the null and go to the alternative in two ways. That means whenever we have higher values, we can reject the null and go to the alternative because it differs from this amount 8,400, right? If your sample mean is like 10,000 or 11,000, 12,000, 20,000, it helps you to reject the null and go to here. Similarly, whenever you have smaller values, if your sample size is getting smaller, sorry, sample mean is getting smaller, like 5,000, 4,000, 3,000, those will also support this alternative, right? Okay. So there are two ways that we can reject the null and go to the alternative. So that's why we call it a two-tailed test, because we can reject the null and go to the alternative in two different ways, right? There are two tails here, right? Two rejection regions. So that is why we call this a two-tailed test. Okay. Now, whether it is a right tail, two-tailed, or left tailed will be important when it comes to um, critical value findings in these questions. I will quickly give you a glimpse, right? If it is a right tail test, okay, okay. right, left, 2, right? Now, in the question, you will be given a thing called the significance level. It is the same as the error that we are allowing, or type 1 error, specifically speaking, right? And it will be given as 5% or 1% or 10%, something like that, right? Now, once that is given, right, let's call it alpha, right, with our usual notation. So if this alpha is given in the question, and if it is a right tail test, you move this whole alpha towards the right and do the calculation. I will tell you how, but just have this in your head, right? You give this whole alpha to the right if it is a right tail test. You give your whole alpha, the error that you allow, to the left if it is a left tail. If it is a two tail, you split your alpha into two parts and give one half to the right and one half to the left. Okay, that's how you do the calculations when it comes to right, left, and two tail tests. So therefore, your critical values will change depending on that. So that's why we need to know where you need to understand how to, you know, categorize your test. Right now, one more note, one more thing I need to tell you. It's 12:51, right? If you have some other class, right? If you have some other class, you can leave this session and join to your regular class that will be at 1 p.m., right? Okay. Now I will carry on maybe till 1:30 today, right? Okay. If you have another class, you can leave this session and join there, right? Okay. Now, um, question number 23, did I give the answer? Yes. Okay, I have given the answer. Okay. Question number 24. Now, this is straightforwardly classify the test as two-tailed, left-tailed, or right-tailed. Okay. Now, to classify it, first you need to write down the null and the alternative. Otherwise, you can't do it, right? Okay. So, 24, first of all, even though it is not asking for me to write it, I have to write it to answer this question, right? In the past, the mean running time for a certain type of flashing battery is 9.2 hours. Okay, so the mean running time was 9.2, so that should go to the 9.2 hours. That should go to the null, right? Now let's see What's happening? The manufacturer has introduced a change in the production method and wants to perform a hypothesis test to determine the mean running time has changed as a result. Note the difference now. He's not, he has introduced a new method, right? A production method. And now he wants to check whether the mean battery life has changed from this 9.2. He's not interested in checking whether the mean time is less than this. He's not interested in checking whether the mean time has been increased from 9.2, but he's interested in whether after introducing his method, it it has changed from 9.2. Okay, so the alternative should look like this, because he's looking for a change, right? He's not caring whether the new in after the new introduction, the mean battery life has decreased or increased. Instead, he's just looking whether it has changed. That means he's looking for this under the alternative. Okay, I think it is clear, right? Now, once you see this, you know what is the test, right? It is the two-tailed test. Now, always remember, when you categorize the test as right, left, or two-tailed, you always have to look at the alternative, right? Because the null always have the equality. It won't help you, right? You always have to look at the alternative. If it says not equal, it is a two-tailed. If it's like this, it is a right-tailed, right? Because higher values of sample mean will support this, right? So you have your tail towards the right. If it is like, if the alternative is like this, That means lower values will support this alternative. That means you have a left tail test. Okay, so um, you always look at the alternative hypothesis when it comes to these questions, right? So the answer is going to be two-tailed test for this. So answer A, 24, answer A. Question number 25. Classify the hypothesis test again as two left or right-tailed, right? The maximum acceptable level of certain toxic chemical in vegetables has been set to 0.2 parts per million. Okay, so this is the amount that is recommended. So that goes to the null. An alternative is the researcher's hypothesis, right? That means what we are testing. A consumer health group measures the level of the chemical in a random sample of tomatoes obtained from one producer to determine whether the mean level of chemicals in these tomatoes exceed the recommended level, right? So exceeds, they are not looking for a change or less, they are looking for exceeds this amount, right? So that means they are looking for mu greater than 0.2, right? When you see this, you can see that you reject the null and go to the alternative with when you get higher values, right? So this is what tailed? A right tailed test. Okay. So the answer is going to be C. 25, answer C. Okay. 26. Classify the hypothesis, again the same thing, right? A manufacturer claims that the mean amount of juice in its 16-ounce bottles is 16.1 ounces. Okay. A consumer advocacy group wants to perform a hypothesis test to determine whether the mean amount is actually less than this. Okay. Now, here, there are two values given just to confuse you, right? Now, a manufacturer claims that the mean amount of juice in its 16-ounce bottles is 16.1 ounces. What is his claim? His claim is the mean amount is 16.1 ounces, right? It's true that his bottles are 16 ounces, right? Okay, so you see that now in bottles they say it's 16 ounces, right? But you can go more, right? Okay, so 16 ounces is up to some level, right? Now what the manufacturer is telling, even though it says 16 ounces, he's telling in his manufactured you know um, juice, right? There are 16.1 ounces, right? A zero point 0.1 ounce more usually, right? Now a consumer advocacy group wants to perform a hypothesis test to determine whether this person is telling the truth or not, right? So they are testing whether the mean amount is actually less than this. Okay. So now if there's more than 16.1 ounces or exactly 16.1 ounces as the manufacturer claims, there's no issue, right? Because there's no problem to the consumer, right? But if there's less, the government should take an action about this company manufacturer, right? Because he's claiming some amount and he's giving less than that to the people, right? So this advocacy group is trying to test that. Okay, so the null and the alternative, right? It's very clear again. Mean is 16.1 ounces, right? 16 doesn't have to do anything here, right? Okay, 16 is just to confuse you. Okay, so the mean amount, the manufacturer is claiming 16.1 ounces in its bottles, but a consumer advocacy group want to test whether the mean amount is actually less than this. So they're testing whether this mean is less than 16.07 ounces. Okay. Okay. Now, what is this test? When you have this mu less than some value, if your alternative looks like this, it is a left tail test. Okay, you can remember it like that, or you can argue and think, right? You reject the null and go to here, right? We have more support to the alternative when you get less values for our test statistic. Okay, because this says mu less than this, so if the sample is giving us smaller values, right, the sample statistics are smaller, then it supports the alternative, right? So we reject the null and go to the alternative when you have smaller values. So your tail is towards the left. Okay, so it is called a left tail test. Okay, right. So question number 26, answer B. Okay, right. So we did 26. Now it's time to go to 27. Now, in the previous three types of questions, right? Simply, if you want to do it quickly, you simply look at the alternative, right? If it is mu naught equal to some value mu naught, it's two-tailed. If it is like mu greater than some value mu naught, it is right-tailed. If the alternative looks like mu less than mu naught, it is left-tailed. Okay. This will help you to answer those questions easily, right? Or you can argue and think, right? From your head, you can say, when do we reject the null and go to here? Okay, if it is for higher values, it should be right tail. If it is for lower values, it should be left tailed. And if you can reject the null in both ways, high and lower values, it should be two tailed, right? Or you can simply remember it like this. Okay. Okay. Right. Next question. Question number 27. Okay. Question number 27 is about yeah, it's about type 1 and type 2 errors. Okay. Now, first of all, I should tell you what type 1 and type 2 errors are. I will tell you very quickly, right? Now, there are two types of errors that we can do when doing a hypothesis test. Why? Because the hypothesis test is based on a sample, right? So based on the sample, we might come to a wrong conclusion. There is a possibility, right? So we have to identify what are these possibilities and try to reduce them as much as possible. At this level, you simply need to identify them. We are not talking about methods of how to reducing these things, right? Reducing these errors, right? That's a higher level thing. But at this level, you should know what are the two types of errors that we can make during a hypothesis test, and depending on that, how to implement that error inwards. That's what these questions are, right? Okay. Now, note that in a hypothesis test, in the end, we can come to two conclusions. There are two conclusions. Either the null is correct or the alternative is correct, right? Now, if the null is correct, there is a way of telling it, right? We say, do not reject the null. Okay. We always write the answer based on this null hypothesis, right? If the null is correct, we don't say null is correct. Instead, we say, do not reject the null. Okay. That's the statistical way of telling it. Okay. Now, what if the alternative is correct? Again, you can say alternative is correct, but in statistical sense, we always write it in terms of the null, right? So if the alternative is correct, we say reject the null. Okay. So those are the two things that can happen in a hypothesis test. Null is correct, that means do not reject the null, or alternative is correct, reject the null. Okay. If you reject the null, that means the alternative is correct, right? Okay. Okay. Now, when we make these two decisions, we make our decision based on the sample things, right? Okay. The sample statistics, the test statistic, right? We haven't fully discussed it yet, but note that we make this conclusion about, this hypothesis tells is about the population, right? Now, this statement about the population is checked using the sample, right? That's how we make the decision. Okay. So now, since we use the sample, we can do errors. Okay. So what are the two errors that we can do? Okay. first is called the type 1 error. Okay. Okay. Type 1 error is reject the null, reject H naught when it is true. That means in the actual population, the null is true. Okay. But accidentally, the sample tells us to reject the null. That means we say the alternative is correct. But the actual thing going on in the population is null is correct. Okay. So this is called the type 1 error. Okay. And what is type 2 error? It's the opposite of this. We do not reject the null. Okay. Now we do not reject the null. That means we are saying based on the sample, we say null is correct. We do not reject the null when it is false. That means actually in the population it is false. Okay. So this is based on sample. Okay. We reject the null. Based on sample, we say null is wrong, right? Reject the null, right? I'm talking about type 1 error now. Okay. But actually in the population, what has happened? When it is true means in the population, the null is true. Okay. So this is the type 1 error. Okay. And the type 2 error is we do not reject the null. That means if you do not reject the null, that means we say the null is correct. This is based on the sample. Okay. This is our decision. But what's going on in the population? When it is false, that means actually in the population, the null is false. That means alternative is the correct one, right? So this is the thing in the population. So this is an error, right? So population, null is wrong. That means alternative is correct in the population. This is the actual thing, right? But based on the sample, we say null is correct. Okay. So those are the two types of errors that we can do. Okay. Right. Now, let's look at the question. 27. So we are given the null and the alternative. Null says mu is 8.4 hours. Alternative says mu is greater than 8.4 hours, right? Explain the meaning of type 2 error. Now you have to write this type 2 error in words for this particular question. Okay. Now remember what is type 2 error? We do not reject the null. This is based on the sample, right? That means we are saying null is correct. But actually, what's going on in the population? Null is false. That means alternative is correct in the population. Okay. Now we have to write this in words now. Okay. So based on the sample, what do we do? Based on the sample, we say this is correct. Mu is 8.4 hours. Okay. But actually, what's going on in the population? Population, actually, this is correct in the population. Okay. We should have taken this, but our sample, accidentally gave us a wrong answer here, right? Okay. A perfect thing would be saying this is correct, right? That means rejecting the null, but we fail to reject the null here, right? Based on the sample. So we do not reject the null, but actually in the population, um, the alternative is correct, right? We do not reject the null means we say null is correct, but actually in the population, alternative is correct. Okay. Okay. Now let's see which wordings will tell this exactly. A type 2 error would occur if in fact mu is 8.4 hours. Okay. But the result of the sampling do not lead to rejection of that fact. No, because the first thing is wrong, right? Because this first part is telling about the actual population, right? If in fact mu is 8.4 hours means in the population, what's happening is it is 8.4 hours. No, it is not the thing that is happening, right? Because in the population, alternative is correct. Under type 2 error, what happens? We do not reject the null. When in the actual population, alternative is correct, right? So in the population, this is what's going on, right? So that is not mentioned properly here, right? It's saying mu is 8.4 in the population. Okay. Note that this first sentence is talking about the actual population, right? Because the next part is talking about the sample, right? But the results from the sampling do not lead to rejection of that fact, right? You don't need to worry about that part. At this point, you know it is wrong, right? B. A type 2 error would occur if in fact mu is greater than 8.4 hours. Yeah, that's good. That's good up to there. But the results of the sampling lead to the conclusion that mu is less than 8.4 hours. Now, note this. You might think, right? You might think this is correct, right? Because the population, in the population, you have mu greater than 8.4. Yes, type 2 error would occur if in fact mu is greater than 8.4 hours. But the results of the sampling lead to the conclusion that mu is less than 8.4. Now, there's some sort of a correction here, right? It's correct up to some extent, but there's something missing. Now, the null says mu is equal to 8.4, right? It's not talking about exactly, it's talking about mu less than thing, right? What about mu is equal to 8.4, right? So this is not the perfect answer, right? Part B is wrong, okay? C, type 2 error would occur if in fact mu is equal to 8.4. From there it is wrong, right? Because in the population, this is, when you're talking about population, this is the thing that should be mentioned, mu greater than 8.4. So this is wrong. D, type 2 error would occur if in fact mu is greater than 8.4 in the population. Good, right? It doesn't say it's the population. You should be able to understand it, right? This first sentence is talking about the population, okay? But the results of the sampling fail to lead to that conclusion. This is the perfect answer. The result from the sampling failed to say that this is the correct thing. That means we are here from the sample. Sample says this is correct, right? So this is the most perfect answer out of these four answers, right? So 27 answer is D. Okay. 28. Mu is 16.1 ounces, says the null, and the alternative says mu is less than 16.1 ounces. Okay. Now, explain the meaning of type 1 error. Now, you need to know what type 1 error means, right? Type 1 error means reject the null when it is true. That's how I remember it, right? That means reject the null based on the sample values, okay? But actually, in the population, the null is true. H naught is true, right? Based on the sample, right? Sample says reject the null. But in the actual population, what do you have? Null is correct. Reject the null means the sample says null is wrong. That means alternative is correct, right? Okay. So the sample says alternative is correct, but in the actual population, null is correct. Okay. So this has to be set in words now, right? Let's see which one tells it the best. Okay. 28. A. A type 1 error would occur if in fact mu is 16.1 ounces. So this is, but the result of the sampling do not lead to that, lead to the rejection of that fact. Okay. A type 1 error would occur if in fact mu is 16.1 ounces. Okay. But the results of the sampling do not lead to reject. Oh, okay. Here's the mistake, right? So mu is 16.1 ounces in the population is correct, right? Because in the actual population, null is correct, right? So this is what's going on in the population, right? But based on the sample, we say this is correct. Okay. So in the population, maybe 16.1 ounces, that part is okay. Next says, but the results of the sampling do not lead to rejection of that fact. That means we do not reject that fact. That means we accept that fact, right? The wordings are very, very confusing here, right? So read very carefully. Do not lead to reject that fact means the sample is also telling this is correct, but that is not happening. That's not what's happening in type 1 error, right? Type 1 error happens if the null is correct in the population, but the sample says null is wrong. That means the alternative is correct. Okay. So this does not tell that. Okay. This says null is correct and the sample is also telling the same thing, right? Sampling do not lead to rejection of that fact. Okay. Means we do not reject that fact means we are telling this is the same thing in the sample. So that is not the error we are looking for, right? Actually, this is not an error, right? What's mentioned here, right? Part B. Type 1 error would occur if in fact mu is less than 16.1 ounces. Now this should be wrong. In the population, this is not what's going on, right? In the population, this is the correct thing. 16.1 ounces equals 16.1 ounces should be there, right? So B is wrong. A type 1 error would occur if in fact mu is equal to 16.1 ounces, but the results of the sampling lead to the conclusion that mu is less than 16.1 ounces. Okay, yes, this is the correct answer. Okay, this is the correct answer that tells everything, right? Okay, so these types of questions you need to read very carefully. Okay, D is wrong because this population mu less than 16.1 ounces is wrong, right? So in the population, this is what's going on, right? Yeah. From the sample, we say this is correct, right? So that's the error, right? That's called the type 1 error, right? So, and it is nicely mentioned in C. So the answer for 28 is C. 29. Right. Determine the critical values for one mean Z test. Right. Now, okay. What we have done up to now in these questions is building up the null and the alternative. Okay. There were questions from that. And then from type 1 error and type 2 error, right? The errors that we can make, right? Now, these parts, right, starting from question number 29, right, we are looking at how to come to these conclusions, right? How to make the conclusion whether the null is correct or alternative is correct. Okay. To make that conclusion, there are two methods. One is called the critical value approach, and the other is called the p-value approach. Okay. There are two methods. Now, in the critical value approach, we compare two values. One is called the critical value, and the other is called the test statistic. Okay. We compare these two values and make our conclusion. Okay. So I will quickly tell you it very quickly, right? Not in detail, right? So there's a thing called this critical value. Let's call it here, right? Critical value is nothing but the starting point of the critical region. Okay. What is the critical region? It is the region that we reject the null. Remember that. Okay. Critical region is the region that we reject the null. So this starting point of the critical region is the critical value. If it is a right tail test, critical value would be somewhere here and the critical region will be to the right. If it is a left tail test, critical value should be somewhere here and the critical region will be to the left. Okay. So let's take one. Just let's focus on one thing now, right? Let's say it is a right tail test, right? So here's the critical value, and these are two values. Okay, so let's say critical value is 1.688, right? Let's say 88. And the test statistic is something you calculate from the sample. And this is also a value, right? Let's say this is 2.01. Okay, now we compare these two values. That means if this test statistic falls here, we reject the null. That's how you make the decision. If the test statistic, let's say 1.26, it's somewhere here, right? Okay, because this starts from 1.88, so the critical region starting point is 1.88, right? That's what this critical value means, right? If the test statistic falls to here, we reject. If the test statistic falls to here, we do not reject. Okay, that's how we make the conclusion, right? That is called the critical value approach. And one ingredient that we need in the critical value approach is the critical value. Okay, we haven't discussed calculation of test statistic yet. I just put some two values just to give you some idea how to make the conclusion, right? So these questions are based on this critical value. Okay, we are not asked to make the final conclusion. Instead, these questions are based on how to finding these critical values. Okay, so p value approach I will discuss it later, right? Okay, I have discussed it in class, right? When it comes to a question, I will quickly explain what p value means, right? Okay, so 29, determine the critical value for one mean z-test. Okay. A left tail test with alpha 0.05. Round your answer to 3 decimal places. Now, how do we find these critical values? Okay. Critical value is the starting point of the critical region. That means the rejection region for the null hypothesis. Okay. Now, this value is based on the significance level given in the question. Significance level is nothing but alpha, right? Okay. In chapter 8 also we found it in chapter 8 we were given the confidence level. From that we found alpha, right? The rest. If 95% confident, 5% is alpha, right? Written as a decimal, 0.05. But here in chapter 9, instead of giving the confidence level, we are straightforwardly given alpha, right? In the name of significance level. Okay. Okay. So right. So in this question, a left tail test here, instead of telling significance level, they are straightforwardly telling alpha, right? So alpha is 0.05. And what kind of a test? Left tail test. Okay, that is important, right? So if it is a left tail test, remember what to do. If it is a left tail test, you find the critical value like this. You give this whole alpha towards the left hand side, 0.05 to the left. Okay, and the value here is going to be the critical value. Okay, now how do you find it? Use the z table. You look for 0.05. Okay, you look for 0.05 and you will see that 0.05, I'm not going to re-explain this again because I explained it on the last day, right? I'm looking for 0.05. It's in between. I cannot exactly find 0.05. Instead, I find 0.0495 and 0.0505. Out of these two, normally I would pick the one that is close to this value I need. But here, there's a tie between these two, right? I cannot exactly find 0.05. I found 0.0495 and 0.0505. The gap is the same. So I cannot ignore any of these. So I have to take both of them, take their z values, which is 1.65, sorry, negative 1.65 and negative 1.64, and take the average of those two. 1.64 plus negative 1.65 divided by 2 will give me negative 1.645. So the critical value will be negative 1.645 for this left tail test. Okay. So for a left tail test, the critical value would be, I can say, always, right? Always negative, right? There might be some cases, but I cannot think of such cases. Like If it is a left tail test, critical value will be negative. If it is a right tail test, the critical value will be positive because this thing will go to the right if it is a right tail test. Okay. If it is a two tail test, you split it into two and there will be two critical values. Okay. Right. So question number 29, answer is A. Question number 30. Question number 29, answer A. Question number 30. Okay. Question number 29, answer is A. Okay. Question number 30. Determine the critical values for a two-tail test. Now it's a two-tail test with alpha 0.1. Okay. Now, in the left tail test, we gave the whole alpha to the right. Sorry, to the left. If it is a right tail test, what we do is we give the whole alpha to the right. If it is a two-tail test, you have to do something more. You have to split your alpha into two parts and give to both sides because it's a two-tail test. Okay. Okay. Now let's see. And you will have two critical values for two-tail test, this point and this point. So there are two values. Okay. Right. A two-tail test with alpha 0.1. Okay. Now the thing is, if it is a two-tail test, you have to split your alpha into two parts, right? Alpha into two parts. That means if you divide it by two, you get 0.05. So you have 0.05 to here, 0.05 to there, right? And you don't need to find both the values because one will be the opposite sign of the other. That means if you find -2 here, you don't need to find the other. It will be +2. If you found that this is +3, you don't need to find this value. It will be -3, right? So you simply need to find one value, right? Now, actually, I'm not going to, I don't, since I have the value previously calculated, right? When I have 0.05 towards the left, the value here is -1.645. I just found it, right? I have to do the same thing to find this here, right? When I have 0.05 to the left, the value here is going to be -1.645. You can use this table and find it, right? And I'm not going to find this since I have this here by symmetry, right? I know that the normal distribution is symmetric, right? So when I have 0.05 probability to the right, the value here is -1.645. And when I have the same probability to the right, this side, the value here should be the opposite sign of it. That means +1.645. Okay. So the critical values are going to be, I can write it plus or minus 1.645. Note that there are two values here, right? Plus 1.645 and minus 1.645. So the answer is B. Okay. Question number 30. Sorry, this is 30, right? 31. Determine the critical value for a right tail test with alpha 0.03. Now, a right tail test, alpha 0.03. If it is a right tail test or a left tail test, you're not going to split your alpha. If it is a left tail test, you give your whole alpha to the left side. If it is a right tail test, you give your whole alpha to the right. So this is 0.03. The value here is what you need. Okay. So when you have 0.03 to this side, you look in the normal table for 0.97. That means 1 minus 0.03. Why? Because the normal table is always going to give the values to the left hand side, right? So you look for 0.97 in the normal table. Okay, 0.97. Okay. .97. Okay. Here are the two values. Okay, 0.96. Sorry. 0.9699 and 0.9706. Okay, so I'm looking for 0.97. I got 0.9699 and 0.9706. Okay, 0.9699 is created by 1.88 and the other by 1.89. Now, out of these two values, there is a clear-cut winner. 0.89699 is much more closer to 0.97 than this guy. So this is out of the way, right? So the answer is going to be simply this, which is 1.88. So the z value there is 1.88. So the answer is B. Okay. Now, okay. Now it's 1:30, but what I can do is there's very few questions left. Okay. Now another thing, I have decided to exclude some parts from this upcoming exam. Okay. So uh, I will discuss only up to question number 38. Okay. So there's, you know, few questions to proceed, right? And if I can get another 30 minutes, I can finish this. Okay. What would you say? Maybe less than 30 minutes, I can do it. Are you all okay if I go on, or do I need to take another session? What do you say? Finish it now. Good. Okay. Right. Let's finish it now then. Okay. Right. Okay. Answers are clear. Okay. Let's finish it. Okay. Okay. Hopefully it will. I can finish it in like 20 minutes. Let's see. Right. Um, 32. Question number 32. Okay. This is about the p-values, right? So the second type, now there are two ways, right? Critical value approach and p-value approach to come to the conclusion, right? Now, okay. Now the next questions, next few questions are on the p-value approach, right? Now, these questions are not about how to finding the p-value. There can be questions of how to finding the p-values, right? We will learn them later, right? Okay. Now, the next few questions are asking you how to make a conclusion based on the p-value. Okay, that means the conclusion is whether to reject the null or do not reject the null. How to make that conclusion using the p-value? You simply have to remember this. If the p-value is less than or equal to significance level alpha, you reject the null. That's all you need to know to answer these few questions. Okay. You compare the p-value straightforwardly with the alpha or the significance level given. If the p-value is less than or equal to that, you reject the null. Otherwise, you do not reject the null. Okay. So question number 32, alpha is zero 0.1, p-value is how much? 0.13. So what can you say? P-value, which is 0.13, is larger than alpha, right? If it is less, we reject. If it is large, therefore we should not reject. That means do not reject the null should be the answer. Okay. So question number 32, there are no A, B's, but I would say B, the second one. Okay. 32, answer is the second one, which is B. Okay. 33, again the same thing. P-value is 0.07, alpha is 0.1, sorry, alpha is 0.01, sorry, alpha is 0.01, I made a mistake. Okay, so alpha is 0.01, p-value 0.07. Which way is it going? It's again this way, right? P-value is higher, 0.07 is higher than 0.01. So if p-value is less than or equal to alpha, we reject. Always remember that. Okay, so if here it's the other way, again do not reject the null. Okay, so the answer for 33 is B again. Okay, B means the second answer. Okay, 34, p-value 0.004, alpha 0.01. Now this is less, right? P-value here is less than 0.01 alpha. Okay, so if the p-value is less than or equal to alpha, we reject the null. So here our conclusion is to reject the null. Okay, so 34, answer A, reject the null hypothesis. Okay, so those three are easy, right? So you simply need to compare those two things. Okay, 35. Right. Now the value obtained for the test statistic z in one mean z test is given. Also given is whether the test is two-tailed, left-tailed, or right-tailed. Determine the p-value to 4 decimal places. Okay, now here's the thing. Okay, I haven't told you how to calculate the test statistic. Okay, now there are two equations to calculate the a thing called the test statistic. Okay, now I'm not gonna focus too much on this because this answer is given here, right? You're not asked to calculate the test statistic in this particular question. So I'm not going to worry about it up to now, right? So I will simply tell you the equation, right? There are two equations like this. One is like this when sigma is known, and there's another one like this when sigma to use when sigma is unknown. Sample standard deviation is known. Okay. Now, this is called the z statistic. This is called the t statistic, t test statistic. Okay. So this the value obtained for the test statistic z, right? That means they are using this equation, right? Okay. Now there are certain questions that you need. There are questions that you need to calculate this test statistic using this formula. But for this, to answer these few questions, you don't need it because they are giving you the answer for this, right? You see, uh, one means z test. The c test statistic is given, right? That means this z value is given. You do all of these, you get the answer as 2.38 for this particular first question. That's what they're saying, right? Instead of asking you to calculate it, they have given it straightforwardly. Okay. Now, what you need to do is to calculate the p-value once you have the test statistic. Okay. Okay. So, what you need to know to answer this question is this. First, understand that there is a quantity called the test statistic that we would calculate using the sample data. Okay. Now, this test statistic, yes, there are two formulas for it. We will do questions from that later on. But up to now, they have done the calculation for you and given that, okay, the test statistic value is this. Now, to answer this question, what you need to know is how to calculate the thing called the p-value using this test statistic. Okay. This is how you do it. If it is a right, again, it will change depending on the type of test. Okay. If it is a right tail test, you calculate the p-value like this. You start from this test statistic value. You start from the test statistic value. Okay. I will say z stat. Okay. You start from there and calculate the area to the right. That will be your p-value. This is your p-value. Okay. If it is a left tail test, you start from the thing called this test statistic, again test statistic value. Okay, z test I would call it, right? And calculate the area to the left. That will be your p-value then. If it is a right tail test, you start from the test statistic, calculate the area to the right. That will be your p-value. If it is a left tail test, you start from the test statistic, you calculate the area to the left. That will be your p-value. Now be careful when it comes to two tail test. Okay. Now, usually for a right tail test, the z test statistic will be positive. For a left tail test, it will be negative. Okay. But for a two tail test, you know that it can be both, right? Plus and minus. So you have to be careful. If you are given the test statistic value as minus, right? Let's say -2, right? You calculate starting from -2 area to the left. If it is a negative value, you calculate area to the left. Okay. But note that if it is a two-tailed test, there is a similar area starting from the positive value of this to the right hand side. Okay, so you find one area, right? One region, one, let's say this is point 2, and there is another point 2 area to the other side. So what you do is you calculate 1 and multiply that by 2 to get the p-value, because there is another similar region to the other side, to the opposite side, for a two-tailed test. Okay, so that's all you need to remember to answer this question. So let's do it now. Okay, question number 35. It's a right tail test. Okay, so therefore, starting from the test statistic value, which is 2.38, you simply need to calculate the area to the right. Why? Because it's a right tail test. Okay, so this is the p-value. How do you do it? Go to the normal table, you look for 2.38. Okay, so if, since it is a z test, you look in the normal table. Okay, 2.38. Now you know the z value, we are looking for the probability. So 2.38 is 0.9913. Okay, so this 0.9913 is not the area we need, because it, the table gives us this part, right? But we need the other half, right? The other side, this part. Okay, so this should be how much? We know that the total area is 1, so 1 minus 0.9913 should give us the rest. That means the area to the right. Okay, so that is what we need as the p-value. So p-value here is going to be 0.0087. So 35 answer is B. Okay, 35, yes, answer B. Okay, 36. Okay, a two-tailed test. Now this is a two-tailed test and z value is 1.31. Okay, so two-tailed test, z value is 1.31. Remember that z value 1.31, it's true that it is positive, but since it is a two-tailed test, oops, since it is a two-tailed test, right? Even though you have 1.31, right? There is another value, negative 1.31, you need to consider, right? Okay, so keep that in mind. Okay, so if it is a two-tailed test, you find the p-value and multiply it by 2 to accompany for the other part, right? Okay, so since this is positive, right, you calculate this region. Okay, keep in mind that there is another similar region starting from 1.31 to this side. Okay, but you have it in mind, and simply what you need to do is find this answer and multiply that by 2. Okay, that will give you the p-value in the end, right? So what is this answer? Let's see it. 1.31. Let's look for 1.31. Okay, 1.31 will give me 0.9049. 0.9049, but this is the area to the left, so I need this part, which is 1 minus 0.9049, which is how much? 0.0951. Okay, so this part is 0.0951. Okay, right, let me write it clearly, right? So this region is 0.0951. Okay, so there is a similar region to the other side. So the p-value is going to be 2 times 0.0951. Always remember, if it is a right tail test, sorry, two tail test, you have to multiply this answer by 2, right? So the final answer would be 0.1902. Okay, so 36. Answer is A. Okay, 36, answer A. Okay, 37. 37 is very similar to 36. Okay, but it's a two-tailed test. But now the z value, you see, it is negative. Okay, in a two-tailed test, z value can be both negative and positive. You know that, right? If a negative value is given in a two-tailed test, that means here you calculate the area to the left, okay, and multiply that by 2. If the z value in a two-tailed test is positive, let's say it's positive 1.07, you start from positive value and calculate the area to the right and multiply that by 2. Okay, this confusion won't happen in, you know, left and right tail test usually, right? In a right tail test, usually this test statistic will be positive. For a left tail test, usually it is negative, right? Okay, but for a two tail test, it can be plus and minus both. So if a negative value is given, you you start from the negative point, you calculate the area to the left and multiply that by 2. Okay, if this thing is positive, if a positive value is given for a two tail test, you start from here. Since it is positive, you calculate the area to the right and multiply that by 2 to accompany it with the other part. Okay, okay, so here negative value is given, so you calculate this area, and to accompany with the right part, you simply multiply this answer by 2 later on after getting the answer, right? So let's find this. Negative 0.17, you look in the z table. Okay, negative 0.17, 0.17 will give me 4364. Sorry, 7, yes, 4325, sorry, 4325. This is the answer, right? So 0.4325. Okay, now note that there's a similar region to this side, so therefore p value is going to be 2 times 0.4325, right? You do this when you have two tail test only, right? Okay, so your final answer would be 0.8650, which is do we have such an answer? Oh yes, 37, sorry, 37, answer D. Okay, 8650. I was looking at 36. Okay, so 37, answer D. Okay, 38, this is the last question. Okay, that I'm going to discuss, and the rest of the review is valid, but it is valid for the final, right? Okay, in the final exam you will see these types of questions. Okay, first I thought about adding these, but now later on I changed my mind, right? I decided to skip the last few, right? And but these will be in the final, so you need to know this. But the thing is, you don't need to know it for this upcoming exam, that's all, right? Okay, you need to know it in the final. Okay, right, 38, the last question. A left tail test with z value negative 0.58, negative 0.58, and it is a left tail test, so you calculate the area to the left. Okay, so negative 0.58, you don't need to do anything, right? You don't need to multiply by 2 or something when it comes to left tail or right tail test, right? So negative 0.58, negative 0.58 is 0.2810, 0.2810, and you don't need to 1 minus or do something like that as well, because it's the exact area we were looking for, right? Okay, if it is a right tail test, note that we are looking for this. So from the table we get this region, so you, to get the other part, you have to 1 minus this answer, right? But here we were looking for this area to the left, and that is exactly what we get from the table. So the p value here is 0.2810, and the answer is D. So 38, answer D. Okay, right. So that's the end of the review. Okay, the rest of the review I will keep it for the final. And for the final, yes, I may give you another review. I'm not sure whether I can discuss fully for the final, but let's see how it goes, right? So, right, this is the end, and you need to know up to here um, till the to write answers for the upcoming exam, right? Okay, right. Any questions up to now? If you have any questions, you can ask. All right. If you have no questions, thank you very much for joining in. And I will post this on YouTube as well so that you can double check, right? Okay. All right. Bye bye.